Hey physics kids, Mrs. Campbell here. In our fourth video on thermodynamics, we're going to talk about pressure, force, and the ideal gas law. If you remember way back to chemistry, when you talked about ideal gases, there's some assumptions we make about ideal gases. Ideal gases, we say, are far apart on average. They really don't interact with each other in terms of forming bonds with each other. When they do collide, those collisions are elastic, which means while they may transfer energy, they don't lose any energy. Now, there are four states of an ideal gas. There's the absolute temperature of the gas, there's the pressure, the volume, and the amount of the gas. And we're going to talk about how those things relate. We've talked about absolute temperature before in our first video and how temperature relates to the kinetic energy of a gas. What we're going to talk about in more detail first is pressure. So where does pressure come from? Pressure comes from collisions, right? As molecules move around their containers, they're moving at high speeds and they collide with themselves, with each other, and with the walls of their container. And every time they collide, right, they exert a force, right? If you collide with something, you can feel the force. And remember from fluids, we said that pressure is equal to force over area. Now, that means that in order to have zero pressure, I have to have zero molecules, right? If I could generate a perfect vacuum where the pressure was zero, right, then I would have to have zero molecules. That's really difficult to achieve. So when we really talk about vacuums, we're talking about imperfect vacuums, vacuums where just the pressure is less than atmospheric pressure. Well, let's talk about forces and pressure. Remember, if there's a pressure differential, there's going to be a net force, right? And we could define that net force in terms of pressure by being the change in pressure times the area. Now, when something is open to the atmosphere, right, there's a hole in the top of my water glass here, then I have equal pressures. I have atmospheric pressure on the outside from the collisions of air in the atmosphere with my cup, and I have collisions inside from the air with the walls of this container pushing out. So it results in an equal pressure. But if I could seal this and I could pump some of the air molecules out, I could generate an imbalance in pressure, and ooh, we should do that in class. Well, if I could get my kids to drink more cans of soda, we're going to do that. Who thought that that would be difficult? Now, if pressure is coming from collisions, then anything we can do to change the number of collisions will change the pressure. So if I increase the frequency, right, more collisions, more pressure. Or if I increase the speed, right, if you run into something and you're going really fast, right, it hurts a lot more than if you were going really slow. So how do I change those thermodynamic variables to change pressure? Well, let's talk about the obvious one, right? Temperature. Right? If we increase temperature, we know that the kinetic energy of the gas goes up, which means the speed goes up, right? We have that VRMS speed equation that relates to the temperature of a gas. So if I increase temperature, right, I increase the speed, right? More speed, ouch, harder collision, and double whammy, more collisions. So temperature is directly proportional to pressure. As I increase temperature, I increase the speed, which results in more collisions with higher speed and more force. Well, what about volume? If I decrease the volume of this ball, oh, what happens to the pressure? Oh, I can feel it because the force is going up. If I decrease volume, I increase pressure. So they are inversely related to each other. Why? Well, if I decrease the volume, right, I've shrunk the space for those molecules to move in, right? So they're more confined, so there's more collisions. If I could expand this ball, right, then there'd be more area for those molecules to roam around in, and they would hit the walls less frequently. So pressure is inversely related to volume. If volume goes up, pressure goes down. If volume goes down, pressure goes up. And last but not least, what about number of molecules? If I put more molecules in this ball, what's going to happen to the pressure? Well, I put too many, right? The ball's going to pop. So that must mean that pressure is directly proportional to the amount of molecules, right? The more molecules I put in, the more collisions I get. The more collisions I get, the more pressure I have. So we can take all of these variables here and put them together into one equation. And you've seen that equation before. It's called the ideal gas law. Now, we're going to look at the ideal gas law two ways. This way, which you've probably not seen before if you've just taken the basic chemistry class, the ideal gas law says that the pressure times the volume is equal to the number of molecules, capital N, times Boltzmann's constant, remember that's that 1.38 times 10 to the negative 23rd, times the temperature in Kelvin. But you've probably seen it in another way, because remember that number of molecules times Boltzmann's constant is equivalent to number of moles times R, the gas constant, 8.31. So we can write this in a way that you've probably seen before in the Puvnert form, PV equals nRT. Now, a couple things about units, right? Units are very important. Just like in fluids, we deal with pressure in pascals. We deal with volume in terms of meter cubed. If we're using little n, then that's number of moles, and our gas constant is 8.31. And of course, always, always, always our temperature is in Kelvin. Now, since PV over NT is equal to this constant, the gas constant, that means that the pressure, volume, amount, and temperature at one condition has to equal the pressure, volume, and amount and temperature at another condition, right? So we could set these two things equal to each other and get rid of that ideal gas law completely, and we get this. And any factor then that remains constant when we're doing some calculations, right, just divides out. So we get rid of the amount and we have the combined gas law. We get rid of the amount and temperature and we have Boyle's law. Or we could get rid of volume and we have pressure over temperature, which is Gay-Lussac's law, or we could have Charles' law, or we could do Avogadro's law. But because these things have to stay constant, I can use the ideal gas law to look at equalities between different conditions. So let's ask some questions. I have two identical cylinders, A and B, and they contain the same type of gas that are at the same pressure. Cylinder A has twice as much gas as cylinder B. So what must be true about the temperature? Pause the video and see if you can figure this out. Well, because volume and pressure were the same, then we have an inverse relationship between the gas and the temperature, right? If we're going to add twice as much amount, right, then we have to decrease the temperature. So the temperature in A has to be less than the temperature at B for the pressure and volume to remain constant. All right, let's try another one. I have my two cylinders A and B again, and they have the same type of gas. This time they're at the same temperature. Cylinder A has twice the volume of cylinder B, but contains half as many molecules as cylinder B. So what's true about the pressure? Pause the video, see if you can get it right. Well, if we rearrange our equation to solve for pressure, right, we have molecules on top and volume on the bottom. So that means that instead of these things working against each other, they they work together or multiply together. So if I have twice the volume and half as many molecules, I'm going to have a quarter of the pressure in A as I do in B. All right, let's do some math. I want to know about the final temperature of this gas if in my initial conditions I have 1.5 meters cubed volume of a gas at 27 degrees Celsius when it's under a pressure of 0.2 times 10 to the 5th pascals. And then I'm going to squeeze the gas till the volume decreases to 0.7 meters cubed and the pressure has gone up to 0.8 times 10 to the 5th pascals. Now, I want the temperature in Celsius, but you cannot work in Celsius when you do this problem. So make sure you convert to Kelvin first. Pause the video, see if you get it right. Well, in this problem, we can just use the combined gas law, right? Pressure, volume over temperature in one condition has to equal pressure, volume, and temperature at the other condition. Again, you have to work in Kelvin, so make sure that you add 273 to that 27 degrees before you do your math, or you're not going to get this right. Now, when we set it up and solve, you should have gotten a Kelvin temperature of 560. But I wanted it in Celsius, so now you got to subtract the 273, and you'll get 287 degrees Celsius. Now, for those of you who didn't convert to Kelvin, you did not get the right answer. And if you don't believe me, because you think I just want you to do extra work, try it and see. All right, one more. I have 2 moles of an ideal gas in a 5-liter vessel at a pressure of 8 times 10 to the 5th pascals, and I want to know what the average kinetic energy of a single gas molecule is. The kinetic energy? What? Oh. Pause the video, see if you can figure out how to solve this. Well, hopefully you remembered that the average kinetic energy of a single gas molecule is related to the temperature of the gas. So we need to use the ideal gas law to find out what the temperature is, and then we can use our kinetic energy equation. So we got to do a little PV equals nRT here. We have moles, we have a pressure in pascals, but notice that the liters, the volume unit is liters, and we need meter cubed. So make sure that you remember there are 1,000 liters per meter cubed. So to calculate the temperature of the gas, right, just plug in your variables, make sure they're in the right units. You should get 241 Kelvin. Now we got to plug that into our average kinetic energy equation. Now in this case, I only asked for the average kinetic energy of a single gas molecule. So you don't have to worry about multiplying by the amount of moles or the number of molecules. So we can just use the equation that says the average kinetic energy of a gas molecule is 3/2 kb times T. So we plug that in to our equation, and you should have gotten about 5 times 10 to the negative 21st joules. How'd you do? See you in class.